Hello, everyone. Welcome you back to study MA4822, which is about the measurement and the sensing system. Today, we move on to study the lecture on measurement of inductance. As usual, before we enter the study of today's lecture, let me give you a quick overview about the answer to these four common questions that you may have in mind. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to study from this course? Question number four, how to learn the knowledge from this course, all right? So let's start with the review about the answer to these four questions. Question number one is about why to study this course. By now, you should know our mission on Earth include number one, to understand the world. Number two, to improve and to change the world. All right. Then how to understand the world? The answer is to discover knowledge. Then how to discover knowledge? The answer is to obtain sensory data. Then how to obtain sensory data? The answer is to make use of measurement and the sensing system. Therefore, you understand this course is very important, okay, to the support of knowledge discovery undertaken by human beings. Then how to improve or change the world? The answer is to invent smart system, smart product, or smart machine. Then how to invent smart product, smart system, and the smart machine? The answer is to incorporate closed loop feedback control system inside this product, inside this machine, and inside this system. Then what is a closed loop control system? A closed loop control system consists of three basic modules or building modules. One of them is the sensor. Therefore, measurement and the sensing system is extremely important to the invention of a smart system, smart product, and smart machine. From this slide, you see we have a smart street light system, smart parking system, smart building system, smart home system, smart environmental system, smart healthcare system, and you also see this big name, Internet of Things. Okay, inside the Internet of Things, the two major devices are sensor and the actuator, right? So now you know the motivation for you to study this course. The second question is about how to study this course. My advice to you is to put yourself into the mindset of a designer. Then with the keyword of a designer, automatically you will raise these four questions. Question number one, who are the user? Question number two, what are the needs from this user? Question number three, what are the functionality of the future product or system that you are going to implement in order to meet the need from this user? Then question number four, what should be the solution behind the design of your future product or your future system, such as a sensor, Internet of Sensor, or Internet of Sensor, all right? So the answer to question number one should be obvious to you. Human being need to have a sensor in order to understand the world. Machine need to have a sensor in order to become intelligent, all right? Then what does it need from human being? What does it need from machine system or product? The answer is to obtain sensory data, all right? Then what should be the functionality of the sensor or sensing system that you are going to design in future? So that answer depends on the specific need from the specific user. For example, sensor needed by vehicle should be different from the sensor needed by smart robot. All right. Then answer to question number 4 should be study this course. At the end of the study of this course, you will know the solution. All right. Then next question is about what are you going to study from this course? Basically, this course will cover the physical principle behind the design of a popular sensor in electric domain, in mechanic domain, in environmental system, and in intelligence system. This course also covers the basic detail about the physical world, the basic detail about the conceptual world. This course also covers the study about this phenomenon of randomness in the physical world. Therefore, you will be able to cope with randomness in the physical world. And also, this course covers some detail about the phenomenon of fuzziness in the physical world. All right. Then the last question you may have in mind is about how to apply learned knowledge from this course. And this slide basically show you the detail about the 2 steps involved in the design of a sensor and the measurement and the sensing system. Step number 1 is to use a sensing element to transform the value on the measurement into readable value. Readable value means computer readable or human readable, right? And here you may face 2 types of physical quantity on the measurement. The first one refer to the situation in which the value of a physical quantity are directly detectable. Then in this case, you just need to use front-end sensing element, all right? And the second situation is in which you will face the value of a physical quantity which are not directly detectable. Then in this case, you have to make use of front-end sensing element followed by back-end sensing element. All right. Then the second step involved in the design of a sensor or measurement and the sensing system is calibration. It is very important for you to do calibration. In this way, the output value will be exactly equal to the input value. In addition, the unit of a measurement of the output will be exactly equal to the unit of a measurement of input. And here, try to remember that we should ignore the unit of a measurement from the value, which are the output from sensing element, because these are the intermediate value inside the sensor or inside the measurement and the sensing system, right? So this slide basically show you the generic guideline for you to apply learned knowledge from this course. Okay, so now we are ready to study this lecture on the measurement of inductance. And inductance is the most important property from the device called inductor. All right, so therefore we need to know what should be the physics behind inductor, what are the important parameters related to inductor, okay? And in particular, we want to know how to indirectly measure the inductance or how to directly measure inductance, okay? So indirect measurement means computation. So we compute the value of inductance from the value of related physical quantity, all right? So let's start with the study of physics behind inductor, right? And first of all, every one of you actually should be familiar with inductor, because I believe most of you know what is a transformer. Transformer consists of one pair of inductor. So we have a primary inductor, secondary inductor, right? So in this way, we can scale up voltage or scale down the voltage. And in the city environment, I believe you may see example of transformer, right? Because this is a device used for the transmission of the power or electric power from one location to another location, right? And another example which should be familiar to you is the electric motor, because I guess every one of you should know what is the electric motor. Then inside electric motor, we have an electromagnet. Then what is the electromagnet? Basically, it is an inductor, all right? So, and this picture basically showing you that we are able to induce magnetic field with the use of a coin. Then the coin basically is an inductor, all right? And here you see another coin. So we use current to induce magnetic field. Then in this way to produce interaction force inside the motor, electric motor. So actually all of you should be familiar with inductor, right? So here, this slide basically shows you the application of making use of an inductor to undertake energy transfer. For example, we have a primary coin. Inside, we have an input energy. Then we have a secondary coin. Inside, we have an output energy. So then you will see we can undertake wireless transfer of electric energy, right? And this is very useful for us to implement wireless charging station for vehicle, for buses, for handphone, for robot, etc. Okay. So this is a typical example of application of making use of an inductor to implement wireless charging station, right? So you see on the ground, we install primary coin, okay? Then at the bottom of a vehicle, we install the secondary coin. Then when the vehicle reach the position, which is above the primary coin, then once we turn on the charging station, then there's a wireless transfer of energy from the ground to the vehicle, all right? So this is a typical scenario of making use of inductor to achieve this application of wireless charging, all right? Then for the buses, so we know the buses always travel between two fixed locations, okay, starting point, destination. Therefore, at these two locations, we can install a primary coin on the ground. So when the bus reaches the destination, then it can take a few minutes to top up the energy, okay? When the bus comes back to the starting position, the bus could also take time to top up the electric energy. So you will see at the starting point, we have a primary coin. At the destination, we have a primary coin, okay? Then at the bottom of the buses, we have an installation of a secondary coin, okay? Then in this way, we can undertake wireless charging, all right? And in the highway, if let's say we ignore the cost, of course, you can imagine if we install the primary coin along a distance of 100 kilometer, 200 kilometer, it will be expensive installation, right? Assume we ignore the cost, but this application offer convenience to the user or to the driver of an electric car, all right? But if let's say the driver could pay the price for doing wireless charging, then the driver could drive the electric car to the recharging lane. Then in this case, the vehicle will be able to top up, okay, the energy while traveling on the recharging lane, okay? But obviously, the driver must pay extra price to the owner of this recharging lane, right? So this is another typical application for you to think about, all right? Then obviously, we can use wireless charging device to charge our handphone, to charge our robot, and to charge our iPad, etc. So this is a toy robot, okay? Then wireless charging for the iPad, wireless charging for the drone flying robot. All right, okay. By now, then, for those of you, if you do not know what is inductor, then this video will help you to understand this simple and powerful device in electric domain.
The purpose of an inductor is to oppose any change in the magnitude of current within a circuit. The electrical property that resists either an increase or decrease in current is known as inductance. An inductor is created when an electrical current flows in a wire wrapped around a magnetic core. You may recognize this as an electromagnet represented by flux lines that develop around the core with the formation of a north and south pole at their respective ends. To demonstrate the properties of an inductor, we'll add a resistance or light bulb to this circuit. As the switch is closed and the current flows through the circuit, the electromagnetic field in the inductor forms and expands rapidly. However, because of the unique properties of an inductor, as the flux lines of the electromagnetic field expands, the changing current generates a voltage that resists the current coming from the source. The maximum opposition to current flow occurs at the instant the switch is closed. Therefore, the bulb will not turn on instantaneously. However, once the electromagnetic field stops expanding based on the level of changing current, the flux will no longer generate an opposing voltage in the circuit. The current will continue to flow and reach its maximum value after 5 time constants, or 5t, where t is equal to L divided by R. The light bulb will then be at its maximum brightness. If you open the switch and stop the flow of current from the source, the electromagnetic field will diminish rapidly and simultaneously release stored energy in the form of voltage. It will actually generate enough voltage to cause a spark across the switch as it opens. Whereas a capacitor uses voltage to store energy, the inductor uses current. Inductance of an inductor is defined as the amount of voltage induced divided by the change in current per second. Therefore, if 1V is induced by a change of 1A in 1 second, there is 1 Henry, 1 H of inductance.
All right, so this video basically showing you the transient response of inductor. For those of you with knowledge about control theory, then it should be easier for you to understand the property of an inductor. So inductor is a dynamic device which has a transient response plus a steady state response. All right. So we make use of a steady state response, okay, to produce electromagnetic field. So this is the working principle of motor, etc. And the inductor also has a transient response. So the video showing you the transient response of an inductor is to induce a voltage which will oppose to the rate change of the current. So therefore, the voltage produced by the inductor is proportional to the rate change of the current. So immediately you understand this dynamic equation. All right. So inductor has a 2 property. One is a steady state response, which is to produce electromagnetic field. Okay, so this is the working principle of motor. All right. Another aspect is the transient response. Okay, so then in this case, then you will see there's a relationship between current and the voltage. All right. Then what should be the definition of an inductor? If we follow the name inductor, therefore easiest way for you to understand the definition is to make this statement, which says that an inductor is a device which could induce a magnetic field. All right, this is one way to define the inductor. But this definition basically emphasizes on the steady-state response of the inductor. All right, and this definition basically emphasizes on the transient response of an inductor. So inductor is a device which will resist to the change rate of electric current. Then how to resist it? Because inductor will produce opposing voltage, which is proportional to the rate change of the current. Okay, so these two definitions will help you to understand both transient response of an inductor and the steady-state response of an inductor. All right, and how to produce inductor? So actually, it's very simple. Inductor means a coin, and you know how to produce a coin with a wire. All right, so you can use a pencil. You wound the wire on the cylindrical surface of the pencil, then you should be able to produce a coin. All right, and this slide basically showing you that we can insert material inside the empty space of the coin. Okay, in this way we could be able to increase the inductance value. Right, so you may have an inductor without the inner material and inductor with the inner material. Right, and since inductor is a standard device inside the design of electronic circuit, therefore we want to know how to graphically represent the presence of inductor. Okay, so this slide basically show you the international convention. Okay, for us to represent inductor inside the design of electronic circuit. Okay, for inductor without the inner material, so we just draw this zigzag symbol, okay, or wave the symbol. It's like a wave on the water surface. All right, and in case we have an iron material which is placed inside the inductor, then we add in these two parallel line. Okay, and if we use ferrite, okay, material, then we use these two dashed parallel line. Okay, dashed line which are parallel. All right, and since the iron core and or inner material we could be changed, because we can linearly change the position of inner material. Then in this way we can change the inductance. Then in this way we produce a variable inductor. Okay, then we need to place arrow symbol on top of the graphic representation of an inductor. All right, so and this slide again summarize the graphic representation. By default, we follow this representation. In case inside the inductor we have an iron core, then we use two parallel solid line. Okay, and if the material is a ferrite core, then we use two dashed parallel line. All right, and if this inductor has a preset value, all right, so then we add in this T symbol on top of the graphic representation of inductor. All right, and if we can change, for example, change the position of an inner material, then in this way we change the inductance value, then we must place this arrow symbol on top of the graphic representation of an inductor. All right, so that's about the basic detail of inductor. Okay, now we look into the parameter which are related to inductor, and obviously you understand that the most important parameter should be inductance. Okay, once we know this parameter, Then subsequently, we can look into more detail about the inner relationship, okay, among all the parameters, and in particular, okay, the dynamic equation, okay, about the circuit which include the presence of inductor, right? So from this slide, you will see inductor is a physical device, then therefore such a physical device may have a physical property such as the length, the diameter, and the cross-sectional area, and the number of the turn. And of course, we can talk about the electric property of an inductor. And then there are three important parameters for the electric property of inductor, right? So one should be the current which flow inside the inductor. Second one should be the voltage, okay, produced by the inductor. And the third one is hidden. The third one should be inductance of the inductor, okay? So these three are the electric property of the inductor. Then the length, number of turn, cross-sectional area are the geometric property of inductor, right? And here you will see for the design of a transformer, this property is very important, okay? So for the input or primary inductor, secondary inductor, so you both of them has this parameter, number of turn, okay? So based on the use of these two values, we can calculate the ratio between the number of a turn from secondary inductor and the number of a turn from the primary inductor, okay? Then we can determine the scaling factor, okay, for the input voltage and the output voltage. If let's say we want to scale up the voltage, then the number of a turn in the secondary inductor should be much, much higher than the number of a coin in the primary inductor, right? So, but for us, because for this course, the focus is on the measurement of inductance. Inductance is the electric property of the inductor, right? So then what is the inductance, right? So inductance basically refers to the ability of this device to induce the amount of magnetic flux, okay, by the applied electric current. So when electric current passes through it, okay, so the magnetic flux will be produced, okay, then there is a constant or coefficient, okay, which will relay the amount of magnetic flux to the applied current, right? So later on we'll show you the equation, right? So then this slide basically show you the equation. So you will see amount of magnetic flux produced by the inductor is proportional to the applied current. So I is applied current to the inductor. Then phi is the amount of magnetic flux produced or induced by the inductor. So they are proportional. This is a linear relationship. Then you see this coefficient. This coefficient is called as inductance, all right, of the inductor, okay? If we compute the first order derivatives, then we have this relationship, all right? For those of you, if you know the working principle of electricity generator, then you will see the rate change of the flux, magnetic flux inside the loop, inside the rotating loop, because we have a rotating loop placed inside the magnetic field. Then when this rotates, the amount of the flux which will pass through the loop will be changing. So then we can talk about the rate change of magnetic flux. This rate change of magnetic flux is actually equal to the induced voltage, all right? So this is the principle from the generator of electricity, all right? So in this case, you will see when we rotate this loop, okay, then voltage will be induced. If we supply this voltage to this load, then this lamp will light up. All right. Okay. So it means this side is equal to the voltage. Then here you see the rate change of current. Another way to interpret this equation is this is opposing voltage produced by inductor, and this voltage is proportional to the rate change of a current. If they say inside this circuit, there's an intention to produce this amount of rate change of a current, then the inductor will oppose it. He will produce voltage. Okay, so try to make this one become zero. Okay, just resist to the change of the current. All right, so you can interpret this equation in this way. All right. So the next question, you may want to know what is the unit of measurement of inductance. Since this phenomenon of making use of a current to induce a magnetic field was discovered by American scientist Joseph Henry, then we use his name to serve as a unit of a measurement of inductance. Then 1 Henry corresponds to 1 voltage induced by the inductor when there is the intention of producing 1 ampere per second. Okay, when the circuit has the intention to produce this rate change of 1 ampere per second, then the inductor will produce 1 watt. Okay, to oppose such a change of current. Okay, then in this case, if this inductor has such a capability, then we call it as an inductor with 1 Henry's of inductance, right? So this corresponds to 1 unit of inductance, all right? Then this slide basically help you to do a revision about the major physical quantity in electric domain, and also try to understand their relationship. For example, voltage is related to electric potential. Some people may use V, some people may use E, all right? So they mean the same thing, all right? Then current is has a unit of measurement of ampere. We use I to represent it. When current pass through resistor, so basically the voltage drop across the resistor divided by the resistance of the resistor equal to the current. Okay, so here we can use voltage or use electric potential, because voltage, electric potential mean the same thing. All right. So then what is resistance? Then resistance from this equation, resistance is equal to the ratio between voltage or electric potential divided by, okay, the current. All right. And then what is the conductance? Okay. So conductance is equal to the inverse of resistance. Resistance means the level of difficulty for the electron to flow through, because the resistor will oppose the movement of the electron. Okay, conductance means the level of facilitation by the conductor. Okay, so the conductor will facilitate the movement of electron inside. All right, or the degree of facilitation to the movement of the electron. So then conductance should be equal to the inverse of resistance. Okay, so equal to I divided by V. Then power is an indicator of electric energy, which is equal to the voltage times current. Voltage times current. Then what is the inductance? Inductance is L. L basically is a capability for this device to induce opposing voltage. That means bigger this value, that means higher will be this voltage. Okay, to oppose the emergence, the appearance of this change rate in current. Okay, when the circuit has this intention of creating such a change rate of the current, then the inductor will produce this opposing voltage. All right, and you will see a bigger L and the larger the opposing voltage. All right, then in the last lecture, we have studied the device of capacitor. Then capacitor has this important parameter, which is called as a capacitance. Okay, so capacitance is equal to the ratio between the charge and the voltage. So basically, capacitance is an indicator about the ability for the device to accumulate or to store electric charge. So you will see this is the electric charge channel is proportional to the voltage. Okay, then in front of it we have this coefficient. So higher this coefficient, that means larger the capability for the storage of charges, right? And it's like the case of resistor. Normally we use color code to indicate the value of inductance, because this is more reliable way for us to indicate the value of inductance. All right, and here you just need to pay attention. We have two versions of color code. One for civilian application, one for military application. For civilian application, this is very much similar to the case of resistor. Okay, so we have the first digit, second digit, third digit, and the fourth digit. And the first digit indicate one number, second digit indicate another number, and the third digit indicate the multiplier. Okay, and the first digit or fourth color indicate the tolerance. Okay, for example, first color is red, then the digit is equal to 2. Second color is violet, then the digit is equal to 7, then it's a 2, 7. And the multiplier is equal to the brown color, then multiplier is 10. So 2, 7 times 10 equal to 270. Then by default, the unit of measurement is micron, Henry. Okay. Tolerance or accuracy is a golden color. Golden color is 5% or plus minus 5%. All right. Then for military version, so you will see this is a indicator, color indicate this device is for military application. Then you have first color indicate the digit before the decimal point. All right. So this one is blue color. Then we have a 6. Then golden color means is a decimal point. Okay, so it's a 6 point. Then this is gray color. Gray color is A. Then we have a 6 point A. All right, so 6 point A, micron, Henry. What is accuracy? Accuracy silver color is this one. So it's plus minus 10%, plus minus 10%. All right, so this is for military version of inductor. All right. Here is one more example for civilian version. Okay, first color indicate digit 2. Second color is violet. Violet means 7. Okay, so digit 7. And this color is brown. Brown color is a multiplier. Multiplier brown color is 10. All right. So therefore, the value should be 270 micron Henry. Tolerance is golden color 5%. That's it. All right. Okay. And in practice, we can construct a network of inductor. And inside the network, there are two basic connections. One is a connection in series, and the other is a connection in parallel. When we connect a series of inductors together, then the equivalent inductance is equal to the sum of the individual inductance, right? We can also connect the inductor in parallel. Then in this case, the inverse of equivalent inductors is equal to the sum of the inverse of the individual inductance. So you have this equation. So this is very much similar to the case of resistor, all right? We can also use inductor to serve as a standard device inside a DC circuit or inside an AC circuit. Okay, so inside the DC circuit, then we will observe this transient response plus steady state response. All right. For example, when we switch to the position 1, then at the early stage, okay, let's say before the settling time, if we use a control theory terminology, that means before the settling time or during the time from 0 to settling time, then we will observe transient response. After settling time, we will observe steady state response. All right. So then here we see the transient response. Then this corresponds to a dynamic system of order 1. So this is the typical behavior of a dynamic system of order 1. And mathematically, it is true because the voltage across, okay, the resistor voltage across the inductor could be A together. Then the sum of these two value is equal to the voltage across the power supply. Okay, so this is the voltage from the power supply. It must equal to the sum of a voltage drop across the resistor and the voltage drop across inductor. Okay, so voltage drop across inductor is equal to the opposing voltage induced, okay, by the inductor, right? Due to the change rate of a current, because when there's a change rate of a current, then inductor will induce this opposing voltage, all right? Then the solution to this derivative or differential equation is equal to this one. So this is a time domain function for I. So you will see when t equal to 0, then you will have 1 minus 0. Okay, 1 minus 1. So initially the current is equal to 1, equal to 0, because when t equal to 0, then this is 1, 1 minus 1 equal to 0. So initial current is equal to 0. Then slowly the current will build up until you reach this steady state response like I0, all right? And when we switch to position 2, then immediately you will see V become a 0, then this become a 0. Then you solve this equation, then you find out the time function for I is this one, okay? When t equal to 0, I equal to I0, then rapidly this will drop to 0, okay? When t is greater than settling time, it becomes a 0, all right? So then from here, immediately you know, if let's say we are able to recall this time response of a current, if we show you this result, then immediately we can calculate, okay, the inductance. For example, here we know the time constant is equal to L divided by R, okay? So inside the power of a natural exponential function, so minus t divided by something, the value in the denominator is equal to the time constant, okay? So the denominator here is L divided by R, all right? So then if let's say we identify the output, which is equal to 63.2% of the steady state response, I0, then the time at which this output occurs should be equal to time constant, right? Which is equal to L divided by R. If we know this value, then immediately we can compute L, all right? So this is an observation for you to use in order to guide the indirect measurement of inductance, all right? And this example showing you more detail about the voltage induced by inductor, okay? For example, we have this RL circuit. Once we switch on, then this system of electronic circuit will have a steady state response and transient response, okay? So this is the transient response. Then after settling time, it will reach the steady state response, all right? So now we want to know what is the time function, okay, of a voltage across inductor, all right? So then we know that, okay, the voltage across the inductor should be proportional to the rate change of current, okay? And the coefficient is equal to the inductance, right? And then from this result, so we know the time function for current is equal to this one. So time function for current equal to this one. Then we substitute I inside here, calculate the first order derivative of this equation, then we obtain this answer. Then from this answer, you will see when T equal to 0, then the voltage, okay, when T equal to 0, the voltage is equal to VB, okay. Then when T increase, then the voltage will drop. So you see this is a transient response of voltage, okay. Then this is a transient response of a current. So this slide basically help you to understand this equation, right? We can also make use of an inductor to build up AC circuit. For example, we may have this pure L circuit with alternating voltage source. This is a voltage source, okay? So, and this slide help you to understand the meaning of a sine function, peak value V0, angular velocity omega, which is equal to 2 pi f. F is a frequency. Frequency is equal to 1 over period. So this is 1 period, okay? So 1 over t, all right? Then what should be the dynamic equation in time domain about this L circuit, all right? So then we just apply this rule, okay? Kirchhoff's voltage rule, okay? So you will see at any point of time, the voltage at this conductor should be equal, okay? They should not have a voltage drop. So therefore, the VT minus VLT, VLT is opposing voltage induced on the inductor, okay? Must equal to 0. Then this one is proportional to the rate change of the current, all right? So both sides times dt, shift this one to the left-hand side, both sides divide by L, then we swap the equality, then we have this equation, okay? And also we compute the integration, then we have this equality. So I is equal to 1 over L integration V, okay, over time, right? And Vt is equal to V0 sine omega t. Then immediately you know, okay, the result should be cos negative or cosine omega t, because derivatives of cosine omega t is equal to negative sine omega t. This is why we must put a negative sign here, right? So then here you have omega, then after integration, so you will have a denominator which will contain omega, all right? So we have this expression. Then from here, immediately you know omega L should be the resistance of the inductor, right? Because this value appear inside the denominator. And then we can rewrite negative cosine omega t as a sine omega t minus 90 degrees. Okay, now you see input is a sine function, output is a sine function. So this is a typical property of LTI, linear time invariant system. For LTI system, if input is a sine function, then output is also a sine function. The only difference will be the change in magnitude and the change in the phase, right? And this change is referred or is due to the resistance, and this change is due to reactance, right? So now you understand the meaning of all these technical terms, impedance, resistance, reactance, etc. Right? So, and this slide basically help you to understand the definition of a resistance of an inductor. Okay, so from previous slide we have this result. Then we have this peak value for current, and the peak value for current is equal to this ratio between voltage divided by a value. Then we can name this value as a resistance of an inductor. So now you know, okay, what is the resistance of an inductor, which is equal to omega L, right? Okay. Then we want to know what is the nature of the phase change. Okay, then in this case, from the time domain function, we compute Laplace transform. So you will see Laplace transform give you a simpler way to understand the physical meaning of this dynamic equation. The Laplace transform, and since in this system, the input is a pure sine function. So it means S equal to 0 plus j omega. So we replace S by 0 plus j omega. Then we have this I j omega V j omega equal to 1 over j omega L. So this basically is a vector in the S-plane or in the phasor diagram. The phasor diagram is a two-dimensional space, all right? So this is the impedance vector. Then this vector has a magnitude. Magnitude is what? Magnitude is resistance. This vector also has a phase. Phase is what? Reactance. Okay. Then from here is 1 over J is equal to negative J, because both sides times J, then J times J equal to negative 1. Right? Then numerator has a J. Negative J means what? Pointing downward is a negative 90 degrees. So it means the current lag voltage by 90 degrees. So this is a reactance, right? Okay, so that's about the physics of inductor and the physics of inductance. And then we are ready to come out the solution for indirect measurement of inductance and come out the solution for direct measurement of inductance. Indirect measurement means computation. Computation means if we know the value of a related physical quantity for whatever reason, then we should be able to compute inductance. All right. So first method is to use this RL circuit. So you see we have a power source, we have a resistor, we have an inductor. Okay. For whatever reason, if let's say we are able to know the sine wave at this point, the sine wave at this point, therefore we just use the peak value, because the peak value will demonstrate the similar relationship like a DC circuit. All right. So from here you will see when we use the peak value, the relationship among the peak value of a voltage, current, and resistance are very much similar to the relationship with the DC circuit channel, right? So this is background knowledge for you to know. So we just use a peak value. Then in this case, we can treat AC circuit like DC circuit, right? So then what will be the resistance of inductor? So resistance of inductor should be equal to the peak value of a V at the point A2 divided by peak value of a current which pass through inductor. Okay. Then what is the peak value of a current which pass through inductor? It should be equal to the peak value of a current which pass through resistor. Then what is the peak value of a current pass through resistor? Answer is VA1 minus VA2 divided by R. Since this is inside the denominator, then we have R divided by VA1 minus VA2. Okay, so once we know resistance of inductor, then what should be the inductance of inductor? Answer is Z divided by omega, because this one equal to omega times L. The inductor's resistance is equal to omega times L. If we know this one, then what is L? Z divided by omega. All right. So we get this answer. So this is a way for us to do the computation. All right. So here we have an example. I split this example into two sub-questions. First sub-question is to compute the amplitude between two vectors. All right. Then subsequently, we can use this result to calculate the inductance, right? For example, we have this RL circuit. So we have R, we have L, okay? And for whatever reason, for example, we know the sine function at the point A1, sine function at the point A2. And we also know the phase difference between these two sine functions. So in S domain, we represent a sine function by a vector. So a vector has a magnitude, has a phase. Okay, so and the vector has a horizontal component, vertical component. For example, we use this vector, okay, voltage to serve as a reference. Okay, so then I represent unit vector in the horizontal direction, J represent unit vector in the vertical direction. So this one only has a horizontal component. Then for VA2, if you have a horizontal component plus vertical component, because A2 has a phase D, okay? Because VA2 will lead VA1 by 56.03 degree, all right? So we have this situation. Then what will be the voltage difference like VA1 minus VA2? Then we need to calculate what should be the magnitude. So obviously, so this is just a simple mathematics law. Okay, how to compute magnitude of the difference between two vectors. So actually the answer is what? Square root the difference in the horizontal component square plus the difference in the vertical component square. All right. So let me simplify it. Then we put in the value. Then we have this expression for this magnitude. All right. So this sub question is prepare you to answer the second question. All right. So let me continue. Now we want to determine the resistance of the inductor if the resistance of this resistor is equal to 1000 ohm, right? Then we apply peak value in this case. So then the inductor's resistance is equal to the voltage, the peak value of voltage at the point A2 divided by the peak value of current. Then this is equal to the peak value at the peak value of voltage at the point A2 divided by R divided by VA1 minus VA2, all right? So therefore, here we need to know, okay, what is the magnitude, because this represents magnitude of vector difference between VA1 and the VA2, because then we use the result from previous question. So it's this one, and the question tell you what is the peak value of voltage at the point A2, and what is the value for the reference resistor. So we just put in the value, then we get this resistance answer. Then what should be the inductance? So inductance is equal to resistance divided by omega. All right. So it's quite straightforward. Then we can also make use of this property to calculate the inductance if we know the time constant tau. Okay, if let's say we know L divided by R, then if we know the value of R, then based on this recoding, we should be able to calculate L. All right, so this is just for you to know. Okay. We can also make use of Priest circuit. Okay, and if let's say one of the device is adjustable, we adjust this Priest circuit, then for whatever reason, now we we know that this Priest circuit is impedance. So it means the voltage difference between this point and this point is equal to 0. Then in this condition, we have this equality because the voltage difference between this point and this point is equal to the voltage at this point, which is equal to this one, minus the voltage at this point, which is equal to this one. Okay, when this is equal to 0, then we have this equality, then cancel out the Vs, then we have this equation. Okay, so inside this equation, if we know the value of 3 devices, then we should be able to calculate the value of the 4 devices. All right, so then here is an example. In this case, so this is Z1, Z2, Z3, Z4. So you see Z2 is equal to R, Z3 is equal to R. All right, so then we have this equality. This is R. Then you will see R times Z4. Okay, will appear here. Then R times Z4 will appear here. So you can cancel out this term. Therefore, you simplify it, you will get this result. All right. Then from here, we want to know what is the Z4. So Z4 is a parallel connection between capacitor and the resistor. Then the equivalent, okay, of resistance should be determined by this equation. So it means inverse of equivalent resistance is equal to the sum of inverse of individual resistance. So this is the inverse of resistance from a capacitor. This is the inverse of a resistance from a resistor. Okay, so then sum of these two values equal to the inverse of equivalent resistance. All right, so then you have 1 over Z4. Then you substitute 1 over Z4 with this result, then merge these two together, then you get this result. Okay, once we know Z1, then what is inductance? All right, so inductance Lx equal to Z1 divided by omega. All right, okay, so that is the way for us to do indirect measurement for inductance if we know the value of related physical quantity. All right, then you may want to know, okay, how to do direct measurement. So this should be the main purpose for you to study this course, because we want to know how to achieve this outcome of doing direct measurement for inductance, right? So then we will follow this principle. The good news is we are able to relate inductance to voltage or current. Since we are able to automatically measure voltage or current, then we should be able to automatically measure inductance, all right? Then how to physically design, okay, the digital measurement and the sensing system for inductance, all right? The answer is provided by this slide, okay? And we leverage on this important observation or background knowledge, which states that all microcontrollers are programmable digital sensor of voltage. Therefore, if we are able to convert or transform inductance into voltage, here voltage means DC voltage, all right? Then we should be able to follow this blueprint to come out your future product of sensor for inductance or future measurement system for inductance, all right? Then the next question should be how to transform inductance into DC voltage. The answer consists of two steps, okay? First step is to convert inductance into AC voltage. Then second step is to convert AC voltage into DC voltage, all right? So in practice, there are plenty of solutions for you to follow. And this slide shows you two solutions for you to convert inductance into AC voltage. For example, you have a power source here, then you have a RL circuit, then the output voltage should be AC voltage. So in this way, the value of a VL contain the value of inductance, okay? Because here, remember, all inside the sensor or inside the sensing and the measurement system, we only use the value of internal physical quantity. We don't care about their unit of measurement, all right? So, and this drawing summarizes like the input-output relationship. So we have an input voltage. Normally this is known because this is the internal physical quantity. This is a inductor under measurement. So therefore we are able to convert inductance into value of voltage. This is the second solution. So you see upper circuit consists of R1, R2, lower circuit consists of two inductor, all right? And this one is under measurement. We supply alternating power source, okay? When we switch on this switch, this could be an electronic switch because the transistor could serve as an electronic switch. So therefore, this switch could be under control of a microcontroller, all right? So we make everything to become automatic. Then obviously you will see the output here is AC voltage, all right? So this is the solution for the first step of conversion. Second step is to convert AC voltage into DC voltage. So actually there are also many solutions. So these two are the popular one. Okay, for example, if let's say we want to just have a rough indication, because since we are able to calibrate the sensor, so it is not necessary for us to do very accurate conversion. But of course, here is better for you to put the capacitor here to smooth out the output to get the DC as output. So this is a solution for us to make use of a half wave formula, okay, from the AC. And normally we are using this solution because this solution we are produce, we are making use of a full waveform, all right? So, and this rectifier, so you will see we make use of 4 diode. Then in this way, we will invert the negative cycle to become positive. So you will see, because this one is just to cut off a negative cycle. Then this one is to invert, okay, negative cycle. Then we make the use of all the cycle here. Then we use this capacitor to smooth out the output. Then you will see the output of the DC is more or less equal to the peak value of AC. All right, so then we know the solution. Once we have the DC, then this could be the input to the microcontroller. Then the microcontroller will convert this input into readable value, readable by computer and readable by human being. All right, then done already. Okay, so this slide basically show you one example. For example, we have an inductor on the measurement. Then we build up this RL circuit with alternating power source. All right, and here you will see we use oscilloscope to monitor this signal. Then you will see this is a pure sine waveform. Okay, then here we can use this as an input to this circuit so as to produce a DC. And in case if let's say you want to scale up the AC voltage, then you can use a transformer. Or if you want to scale down the AC voltage, you can also use a transformer. Then you let it to pass through this diode circuit. Then output should be DC. Always remember we must put the capacitor here, okay, to smooth out the DC. Done already. All right. So then with all these solution put together, you should be able to come out measurement and the sensing system for inductor. All right. And after that, always remember to do calibration. Then the purpose of calibration is to make sure that the output ZI is exactly equal to input XI. And here we will ignore the unit of a measurement of a YI. And after calibration, the relationship between XI and the ZI should follow this straight line. This straight line will have an angle of a 45 degree with the horizontal axis. All right. So, and also after calibration, try to do experiment in order to come out these indicator about or which are related to error analysis, because the user of your product or your system may want to know this value, or the buyer of your product or your system may want to know this value. So this is why it's important for you to do error analysis in order to come out the value for systematic error, repeatability error, accuracy, and hysteresis error. Okay, so you must do this error analysis. Okay, because the buyer or user of your sensor or measurement and the sensing system need to know this value. All right. Okay, so that's all about the study of this lecture, which is on measurement of inductance. All right, and the key takeaway from this lecture is for you to know the physics behind inductor, the physics behind inductance, and also some practical solution for you to undertake indirect measurement, which is a computation. And most importantly, we know how to leverage on the use of a microcontroller to come out the solution which will support direct measurement or automatic measurement of inductance. All right. Thank you for your attention, and I'm looking forward to seeing you in the study of next lecture.